As Richard points out, I am a frustrated archaeologist. I studied history at school and got the history prize from my school. I wanted to be an archaeologist. My mum told me to get a proper job. So I became an engineer like my dad, unfortunately. Fortunately, from the point of view. But thankfully, I've found my way into metrology, which is essentially a smorgasbord of everything. So anyway, I started the biometrology research group at Huddersfield. We're part of, this is where it gets a bit weird. We've got lots of badges that essentially are all the same place. So I started the Centre for Biointerface Engineering a little over a year ago. That basically brings together what we're doing in biometrology with some of the microbiology stuff that I've been involved with as well. So I have biologists in my group, and they generally turn up in white coats that are not very clean. I'm also part of the EPSRC Future Metrology Hub, the Centre for Precision Technology. The Centre for Precision Technology is actually an institute, but we didn't want to change the name. And we're all based at the University of Huddersfield. But essentially, the Future Metrology Hub is a big EPSRC funded hub and spoke project involving ourselves, NPL, Bath, Loughborough and Sheffield, with the majority of the work going on in Huddersfield. Okay, let's hope this clicker works. It's not working. That's going to be fun. Okay. Wow. Anything works. Does anything work? There we go. Let's answer. So essentially, the Metrology Hub has support from 5 catapult centres. So for AMRC, Nuclear AMRC, MTC, the National Composite Centre and CPI. We have commitments from, or at the outset, we have commitments from 29 companies across various areas of industry. And this is sort of the level of support that is involved in the project. So this is, oh, I'm being, hang on.
Slides are not moving online.
Slides are not moving online.
I just need to change the, yeah.
Okay. I did say that if all else went wrong, I would do balloon animals. So we'll see how it goes. Is that working now? This still isn't working. This mainly new battery. Okay. Okay, so the sort of, we're talking about metrology, but what are we talking about? We're talking about various scales of structures. So from, we're sort of not talking about aircraft wings. We let Bath do that, okay? What we're talking about is everything from sort of millimeter, macro kind of range, down to nano sort of level stuff. And I was talking to Richard earlier about how one of my most hated words is nanotechnology, okay? But one of my most hated words, it's up there with machine learning, okay? And I'll talk about additive manufacturing in a minute. But these are things that just give me money. I put the word into the proposal, okay? And nanotechnology used to, when I started as an RF, that was it. Just put nanotechnology in the proposal, you'll get money. And essentially, most of it was nonsense. But we look at structures, different surfaces. What we want to be able to measure them. What we're really interested in is function. Okay, it's not just measuring it, getting a number, getting a pretty picture. Pretty picture is good. You'll see some good pictures in this presentation. But what we want to understand is the function of what we're seeing, and what we're seeing means for the function of the particular component or device. And an idea of a really challenging, really difficult problem, okay? Those of you who are in STEM involved, it's something like this, where we've got these sort of micro needles for subcutaneous drug delivery. How the hell do you measure that? How do you characterize that? That is, what do you even use? Well, the guy looking at it going, yep, that looks interesting. Looks like an army of penguins without heads or something. I don't know what it is. It's a very odd, very difficult to measure thing. But what you're interested in here is, okay, what is the form of it? What is the, are they in the right place? What's the pattern? What is it I need to know about this? This is not a defined function, but how do I deal with that? And these are sort of the, I love SEMs because essentially it's just a really posh camera. But yeah, how do I deal with that? Okay. So the Centre for Environment Space Engineering, we do a lot of different things at Huddersfield. We do, you know, sensors, sensor development, calibration, lasers, all sorts of strange things. Okay. But what I thought I'd talk about is probably things that are more related to things. Can I get rid of this thing at the top? Because it's really annoying. Can I get rid of this? Can I? No, if it's better. It's all right. You don't need to see the title. Right. So I just thought I'd talk about some of the stuff we do more related to bio stuff. And so a lot of what I've been involved with, my PhD was revolving around, was actually 80% biomechanics, but the rest of it was to do with wear measurement. And I've sort of developed a lot of projects involving wear measurement over the years, to the point where we've pretty much measured most of the bits that can get wear or damage or corrosion in the hip, some of the knee, and other things as well. And despite the fact that what happened with metal on metal hips was terrible, it would actually cause us to do an awful lot of research and an awful lot of work in that particular area. And so whether it's looking at using CT to look at, I don't even know what we're looking at there, probably adhesion. We're looking at wear of both hip surfaces here. Here we've got one of these wonderful modular neck components that you get 100% failure on. So we kind of measured them and then went, well, why bother? They're all going to fail. We measured the modular taper surfaces, both male and female, in the hip as well. We started looking at these weird additive osseointegration surfaces, and even looked at the surface of replacement articular cartilage. This was actually a project where we were looking at producing what's the word? Replacement cartilage using spider silk. Okay, we're weaving cartilage using spider silk. This was one of Liam's projects that we did that. And then we've looked at the people who are interested in scenery. We can probably tell you which the best steam cream is and why they like it as well by looking at the surface of skin. We've done strange things with that as well. So a little bit of history. Who's old enough to remember this? Anybody old enough to remember this? Yes, thank you, Claire. Right, okay. Go watch Newman and Baddiel, put history today. It's hilarious. It wouldn't be on telling you. It's that bad. So, a little bit of history. So, when we started the biometrology group, these are three of my colleagues. Actually, only Ahmed still works with me. So, I started the biometrology group about 10 years ago now. And this is kind of how seriously we take things. Okay, a bit of hear no evil, see no evil, speak no evil. And the three wise monkeys. And we sort of started the group with a view to really following on work that we started doing in wear measurement. And I don't know how much you guys know about wear characterization, but certainly at the time of metal on metal blowing up between sort of 2010, well, 2009, 2012, there were lots of big meetings in 2011 where people were yelling at each other. Essentially, lots of different people trying to do it. I'm sure you see it with biomechanics as well, where people are trying to do like define biomechanics of the ear as this, but this is what ISO says it's only fit. Yes, but I don't agree. And so you have different people arguing different things, okay, at the time. And some of it's good, some of it's terrible, and some of it's really bad, okay? And so what we found was there were lots of different studies looking at wear, particularly in retrieved hips. Some of them were performed by clinicians, which is interesting. Some of them are bioengineers, and pretty much a lot of them, it was like, have you ever seen a measurement machine before? Seriously. It was, some of them were good, don't get me wrong. Some of them were trying really hard, and some of them were awful. There were also, because it was an area of litigation at the time, because everyone was being sued, or everyone thought they were being sued, and everybody ended up getting sued. People who were on particular sides of this argument, particularly on the plaintiff side, were very loud. Okay, and this then causes, you can't have a sensible scientific discussion. People start to get absurd. And what this basically showed that we needed standardized approaches. Okay, we needed standardized approaches to weigh measurement. And we're sort of looking at what happens in all these different interfaces that we've got here. Now, what was fairly clear, and I think everyone can kind of agree, is that wear is a significant factor of failure in most cases. It's not entirely the case because people have different reactions to wear neighboring, obviously. And metal ions, you get stories of people who have a reaction to a very low metal ion level, and then you have people who are actually having hips taken out because their metal ions are so freakishly high, it may be messing with their body chemistry in other ways, but they're absolutely perfectly happy. And as far as they're happy, their hips are okay. And then when they're taken out, it's like the top. So it really does depend. Okay. And one question that's always asked is it the surgeon's fault? Now, Alex DeHart did this study a few years ago, looking at the connection between well-functioning painful hips and angled implantation using Lunit's safe zone. And he basically looked at it and went, yeah, I can't really tell. So it's not, is it ever the surgeon's fault? Well, it kind of depends on the surgeon, if I'm honest. So this is myself and Radu, who works with me, being given a crash course on how to implant a hip. This is kind of the testy strength machine on the Ceramtech stand at American Academy. Okay, so you can go and you can see if you can hit the head with the right level of force to actually implant it properly. What we found was there were these very macho American surgeons running up, it was like, a big run up. It was like someone who runs out the pitch to take a penalty. And they'd smack it and it'd be rubbish. You get someone like John Skinner from Royal National Orthopaedic Hospital, just walk up to it, be like a golf swing. Dum. Perfect. And it's all about technique, it's all about experience. Okay. And probably about not eating so much red meat. But what we found that day was that neither Radu nor myself was a very good surgeon. And so we won't be doing any of this. And so what we did in 2012, as a response to all of this, we came up with the first validated method for retrieving wear measurement for bearing surfaces. Okay, but we came up with kind of a list of guidelines. Okay, the things that must be included, and also how this relates to current ISO standards at the time. And so this was kind of very long, very boring paper. Anyone who has the misfortune to read it, it's very worthy. Don't get me wrong. I wrote it, so I'm allowed to slag it off. But I do get a lot of calls from people going, "I got to like page 3 and I fell asleep." So yeah, don't feel bad about that. And so what we did with this kind of then formed the start of a standards effort, and this formed the basis of the ASTM standard guide for measurement and wear for metal metal. And so this formed the basis for the standard guide. And then once we got the standard guide approved by ASTM, our data was then used for the round robin as well. So I know Leeds took part in that round robin. I think Mazen was involved in that. And so what we found was that even when we prescribe exactly how to do the measurement, we couldn't prescribe exactly how to do the analysis. we can only give guidelines for the analysis because everyone works in slightly different ways. What we found was if you want it to fail, you can still make it fail. So there was one outlying lab, not on this side of the Atlantic, who still measured things very, very badly. But anyway, that's now a standard. That's working its way through the standards process in the States. And what we found was essentially that pre-wear definition is really critical. So you can look at this image on the left-hand side, and you can see that, okay, this looks okay. We've got wear on here. You see wear is roughly where we think it would be. Our radius is, it's within spec. That's good. That means it's probably right. And this gives us a wear volume of 10 cubic mil. Seems reasonable, yeah? This has started working, by the way. I don't know what. But if we look at we kind of look at this histogram here, this looks like it's not fitted very well because we've not got a very tight definition of where our unworn surface is. And so if we finesse our fit a bit better so that we've got a much tighter histogram, okay, we've got a much better fit for our unworn surface, what we actually find, we're still well within spec, but we actually find our wear volumes a lot larger because we got the damn size wrong in the first place. Okay, which is a slight problem if you make an error, because that's a 13-fold increase in wear. And so this is why it's important. This is why I presented the raw colours as soon as this before. Of course, big argument, but yeah, these things happen. One of the other things that was we find with you know, again, there's been lots of work done here looking at edge wear, creating edge wear, particularly in simulation. And we see edge wear all the time in retrievals. So it happens. And so what we were trying to do is we're working with Mazen when he was here, looking at right, how do we measure this? Because this is like really weird. It's okay when it's on bare research, you know what bare research is. But when you go over the edge, that edge geometry is often uncontrolled. It's often an uncontrolled part of the geometry. It's like, if you look on the engineering drawing, it's almost like a shrug of the shoulders at that point. And so, again, we managed to come up with a way of segmenting the surface and using surface metrology to actually highlight this wear mechanism, this sort of smearing wear mechanism as well, and be able to basically segment it and then reconstruct essentially what's this weird toroidal freeform surface. And we've now been asked by ISO to do more work on this using, I think, components that Oscar had run here. The man with 3 surnames. Oscar is why I like Oscar. Sorry, yeah, I get them the wrong way around. But he did some good work here looking at simulation of edge wear, different angles of attack. And so we're actually using some of these components to do the ISO work for producing the first draft of the standard for that. And so that's good. That's work we've got going on currently if we ever receive the component from you. Another problem we've looked at is taper wear. Okay, so taper wear, you know, I'm not going to go on about wear. And so we've got this kind of fretting corrosion at the taper, at the modular taper. And if you talk to a lot of engineers that aren't involved in orthopedics, they think that these tapers are mental and why we got them. And then you have to talk about the history of why it exists. And so what we've done is we created a method where we basically take vertical traces of the taper to basically identify our wear scar. And we roll this out into a map so you can identify worn or corroded, and don't get me into that terminology debate because that's an hour-long lecture in itself. So we've got deposits, we've got material loss, as I prefer to call it, and then we've got virgin surface. And what we do is we use that to then use a out of 5-stone technique, which was, 1930s technology, to essentially figure out what the wall volume is. And even though this is about 7 years old, I think this animation still works. So let's have a go. There we go. Right. So really crap 7-year-old technology, but it still works. And so what we do is manage to retain our cylindrical coordinates at work when we're doing this. And so this then gives a true volume loss calculation. It's really good, like Windows 7 and graphics. It is what it is. Okay. But then we have another problem. So we have another problem in that, okay, we've got the female taper is generally just plain sheet. So that's relatively easy to deal with. But then we've got these kind of highly grooved surfaces on the male taper. And how do we classify them? And when we're looking at tapers, generally we use what we call the Goldberg visual scoring technique to go, okay, well, how badly corroded is that taper? And it's entirely subjective and related to how well clean it is. Okay, so there is correlation between material loss and Goldberg scoring, but it's not great, if I'm honest. And so what we did, and this is a PhD that finished, well, he graduated in March, so not that long ago, where we actually managed to take away the periodicity of the surface. We can actually we can actually remove that level of form from the surface to deal with, so we can basically look at what we call the residual surface. And so we can use this to look at material loss. Now, I don't know if any of you have ever seen a stem taken out before, but generally, and this is the confounding factor, they may use a pair of pliers for that. And they may grab the surface that you want to look at with the pair of pliers when it's out. And so they're pliers. Okay? That's technology as well. But when you've got a surface that hasn't been grabbed by a pair of pliers, and you can actually look at it, this works perfectly well. And that was shout out to Zimmer who supported that work as well. But what we're kind of more known for at Huddersfield is surface characterization, surface topography. We literally wrote the same for aerial surface topography. Okay, so and if you're looking at sort of, we don't like to call it 3D as well. It is 3D, but we can't say it's not. It's 2.5. We call it aerial. So when you're looking at surfaces like this, so what this was something I presented. Right here. We just did and literally I measured this on the CMM and then got a black marker and drew a line. Okay. And then took surface measurements next to the line, so I knew where they were. Okay, very high tech. Very high tech. It was 2011, right? That's all I'm going to say about that. Standard existence. And so this is looking at, if you like, the evolution of wear and topography, okay, relative to areas of volumetric. But kind of the orange peel kind of effect you can see, here we go, here, which we've seen before. We've got the main area of centre of the wear area, which is actually relatively highly polished. You've got identifiable edge areas as well. You've got scratching, you've got multi-directional, unidirectional, whatever, as you'd expect. Now, PhD student of mine, Joe Pashley, just started working in the field in September. September? Wasn't September, it was January. He took this a stage further in the fact that he produced the world's longest surface maps. Okay. So if you read his paper, like down the side of the page, you'll see the picture. Okay, but essentially what he's done is he's managed to perform a raster relative to wear area. And he's created an indexing. He created an indexing fixture and technique where you could actually basically take a component from the coordinate measuring machine, put it onto the surface and do color registration. And so that actually is really valuable because now we can not use a black pen and really accurately map the two against each other. This was presented in Glasgow a month or two ago, and it's I don't know if it's in press or in final review for the journal. Anyway, it's going to the journal. So, okay, and then this is where we want to get to. Okay, we're sort of here, but it involves talking to people who've got medical data, which is not always easy. And so then you're trying to correlate all this back to anatomical position. You're trying to talk to people who've done biomechanics, gait, stuff like that. This is where we want to get to. Okay, this is possible, but we need to talk to people who do pre-op and stuff like that. Right, so the second thing I wanted to talk about is additive manufacturing. Now, the reason that Derek Zoolander is up there, okay? You know Derek Zoolander, or is this another one that is going over people's heads? Anyone know Zoolander? Right. So additive manufacturing is so painfully cool, right? Hence the picture. That's, you know, I don't, if I start looking like that when I'm talking about it, somebody hit me. For God's sake. You know, additive, you are so cool. You're like, all right. You know, no socks. So it's got amazing potential, you know, it's got amazing potential, but it terrifies me and I use it, right? It terrifies me. AM terrifies me. And I'm doing everything I can to make it better. So we know mass customization, everyone likes these things that look like chewing gum that's been left on the radiator, okay? It's just melted and made a mess. But it's like, that's a component. That's the design for our new component. It's melted chewing gum. Look at some of these. Like Harry Redknapp's face. It just looks wrong, you know? It just looks wrong. And what it gives us these amazing things. We can look at very, very complex topologies. We get massive increase in strength to weight ratio. With the downside or the upside or whatever side you want to look at it, but we've got features that are definitely non-standard GD&T. How the hell do you look at that and say this is right? Okay? And everybody's doing it. Okay? So this was Wohlers who made the big AM what's the word? Bible, you know, every year. In 2014, they were projecting sort of 20 billion in AM revenue by 2020. They didn't obviously foresee the pandemic. Okay. Actually, 2020 was about 12 billion, but we are forecasting 78 billion by 2028. This is where the money is. Okay, this is where the development is. Everybody's doing this. Okay, there is so much work in this area, and it's got all these massive, you know, all these words, lots of words, right? Okay, it's very industry 4.5. It just is, and we already have, you know, established uses. So, you know, we've got to tie it together with imaging. If we're going to talk about using it, medical devices, we want to look at imaging as well. So we can already look at things like, okay, what size of acetabular components required, what's stem size, leg length discrepancy, we know this, okay? And people are already using 3D printer models in complex cases. I've seen these in case reviews in RNOH. And this is helping to plan surgery. It's also helping to plan outcomes. It's helping to understand. And it's a great thing when you've got surgeons and you've got engineers working together. Everybody becomes more literate. You know, I used to work for a small engineering company while I was putting myself through my master's course. We used to make firefighting equipment. foundry, machine shop, only three of them. And but it was like a little bit, everyone's slightly close to reality, okay, from each other. Bit up. And then you sort of look at that and compare it to, okay, this is kind of, we need to be able to talk the same language. This back in the 1990s, so before. And people didn't talk the same language, you know. We're still talking about getting CAD and CNC to work properly. That's how all that. But yeah, I mean, back then the drawing office was like a whole different place. But now what we're trying to do is we're trying to bring people from very, very different backgrounds to be able to talk the same language, or at least a version of Esperanto that allows you to understand it. Yeah. Because I didn't do biology at all. I didn't do Latin. So some of these words are quite confusing. Most of that is a reproduction from PhD. But or at least part of it, you know. But you know, it's you need some level of understanding. In the same way that a design engineer doesn't really understand necessarily which body part goes where. When you try talking to a surgeon about lubrication, unless they do something on the weekend, they're not going to understand it. So you know, it can be confusing. So anyway, so it's used for preoperative planning. We know it's also used for trauma implants. Here we got, you know, cranial surgery implants. We'll talk a little bit more about in a bit from Rationale, and also a thing from EOS, which essentially is looking at a reconstruction of an acetabulum, probably due to bone cancer. This is something similar to, we worked on something similar with the Pew. On this, we call them the kind of fried eggs, because essentially it looks a bit like a fried egg. You know, you drop an egg in a pan, it always looks different. The yolks up there, there. But depending on what the patient is, it will essentially look like that. And what you're doing is you're trying to create the geometry that then a standard component will fit into. That's you know, that's sort of a way where you can see an immediate use for AF in implants. Where I have a little bit more abstraction is when we're sort of talking about standard implants, maybe, or a standard implant geometry. Now, every human body is different. Yeah? We aren't all Australian Olympic swimmers. Okay? And we want implants to fit well, you know, fit perfectly. I'm going to ask you a question about that in a minute, actually. Do we want them to fit perfectly well? Because if they fit too well, you'll never get the damn things out, right? That's a separate issue. We may come back to that. Now, we want to be able to produce small quantities, one-offs or thereabouts, at reasonable prices. Lots of question marks. And we have this ability to create these lattice structures, okay, that can promote bone growth. And everybody always talks about these from an osseointegration perspective. I look at them slightly differently. I look at them as like, holy cow, don't sneeze in that, you're never getting that infection out. Yeah? I just look at that as a site of infection. And it worries me. Now, I don't think we've had manufacturing failures, but I have a PhD working on this just to check. Okay? That's what he does. So he recreates these and then sneezes on them. We use bioreactor experiments. We've got 4D CT and it's you know, full 9 yards. So yeah, that just worries me. This interplay between osseointegration and infection. I remember I was at a meeting. I was at a meeting at UCL, and I was there to see Alistair Hart and John Skinner. And John came running in, and he'd just come from the hips side of it, where they talked about the prevalence of infection in hips and the fact that it was stubborn never shift. No matter what we do, no matter how clean we are, no matter how lovely we are, no matter how good our hospitals are, there's suddenly the same percentage of failures due to infection. What the hell do we do? We need a plan. And it got me thinking, and it was like, okay, well, why is that? What is it about what we're doing? What is it about the surfaces? What is it about the components? What is it about any of it? And why is nothing we're doing working? We'll come back to it. Now, the other thing about, and this is kind of a bit like doing as well. The other thing about additive manufacturing, you can do these really strange, weird structures. Now, ideally, bone is the best structure for carrying load in the body. Why don't we recreate bone? You know, why doesn't our implant mimic bone? That would be the ideal. We don't want stress shielding. We want more bone or equivalent. So why don't we look at some sort of structure? Because bone is brilliant. Bone is brilliant. It models based on stress and load. Okay, it's perfect material. So why don't we do that? Okay. Is this an idealized orthopedic situation? Or if you create something that's too good, you can never get it out again. Okay. So, boring metrology bit. So essentially, when we look at metrology and we're looking at design, we assess things based on size and flatness, straightness, and all these kind of things we can fit geometric, what we call geometric proof. Okay? And so we have all these different GET things that we do. Runouts, which people understand or don't understand. But I think everyone understands parallelism, perpendicularity, and stuff like this. But the problem is we're designing things that don't fit any of this. Okay? We're designing stuff that looks like that. Okay? And this is completely non-GPS compliant. And how do you specify the test for compliance if you're essentially designing a bird sensor? Yeah. We've got structures that are defined by stress and load path. They're defined by function. Okay. And once we've got some sort of data set, how the hell do we deal with it? Okay. Now we can do some sort of CT comparison to CAD, and does it do that? But that's like just switching your brain off about it. It's going to be an answer. What? You know, it just gives you a number. It's like, well, what is that? What does it mean? And so we need to understand what we call design intent. So what was the intent of our design? What do we want it to do? What's the function? Okay. And then how the hell, if we've got, you know, we're talking about osseointegration, we're talking about things in a minute, we're talking about heat transfer. You know, surface is very, very important for that. How the hell do we get the surface for that? That's hard. That's really hard. Okay. Now, to truly harness AM, what we need to do is to optimize design. Okay, we want to look at functional constraints and limits. And so what we've done here, we want to look at mechanical stress or thermal stress, whatever. What I've done here is it was a student, actually a final year student who did a PhD who took a design of it. Some of you may recognize it, I'm not going to mention any names. And he just applied let's apply some relatively, let's apply an axial load. Let's not do anything too complicated with it. Let's just look at it from a stress point of view, pure axial loading. Okay, and then let's create a lattice structure, and then let's modify that lattice structure as we'd expect a bone to modify based on where the areas of stress are. And so this is essentially topology optimization, but not use entomology to train this. And so this design now is not based on geometry, although it has a generic geometry to it. This is based on function and the function that we're trying to achieve. And the other thing to understand is there's not necessarily a single correct answer. You know, if you have a couple of broken structures, that just means you need material outside to compensate. And Eunice actually did this. This is a final year project in about 2018. And he actually won the design award for this. I was like, ever so like proud dad for that, I'd say. International award. And I just thought, it was kind of a whimsical kind of project, and I just sort of thought, he's a bright kid. He started the National Additive Manufacturing Society with guys at Cambridge, and let's see what he can do. Essentially. And so this is interesting. I mean, it looks like, you know, made out of Rice Krispies, but essentially it's an interesting thought. It's an interesting contribution to the debate. That's what we'll say. And so when we're looking at AM, we've got, holy cow, a lot of things that we need to talk about that could go wrong that we have to understand. Okay, there are lots of moving parts. This isn't CNC machining. This is, we got a lot of things coming into the system here. A lot of different things you can change, whether it's like material, whether it's like manufacturing, and it can basically lead to nonsense at the end. What we're trying to do is create something that's very, very complex. And these trabecular structures, really, we can only really look at them with CT. We can only really analyze them with CT because we want to look inside something. And you've got a choice. You either do destructive testing or you use CT. Now, what we find is we find areas of porosity. Porosity is a problem because we're forming from powder. Okay, this doesn't start out as solid. It starts out as powder. And so we get porosity, and this then causes compromise our integrity. And what we find is there's a relationship between our standard build parameters. And we have to understand that because this isn't solid, and again, we have to understand that there has to be an acceptable defect size. We are never going to have a part with no defects. Okay? And again, that relates back to our design intent. We can't avoid defects on boards. You can do post-processing, so you can do hipping and things like that. But for structures like this, that's very, very difficult to control. And again, this is as an effect on fatigue as well, whether it's mechanical or thermal. And so this is a sort of concept design we've come up with. This is something we're working on with Cairo University at the moment, their Memphis school, looking at reconstructive maxillofacial. Essentially, the original concept was for someone who's recovered from surgery. But this is, you know, basically just showing you, A, that you've still got semi-melted powder all over your build, and what the sort of complexity of our lattices, or irregular lattices are. Okay, this is something that's ongoing. This has been presented a few times. It was presented to the president at one point, I think, not by me, thankfully. But yeah, so that's something that we're working on at the moment as well. So how do we ensure quality? These things look really, really hard to measure, so I don't know the right. So we need to be able to image critical features. We need to have tools with sufficient resolution, sufficient accuracy to do this with certainty. We need a manufacturing system that is either repeatable or at least is predictable. And that's, you know, predictable stupidity is better than unpredictable intelligence. And so one of the things we do at Huddersfield is we create in situ metrology. So we create these, working with Wayland Additive, who are an additive manufacturing company. We work with Rationale as well, but this particular project is with Wayland. Where we're looking at sort of in situ metrology. So we're looking at actually monitoring the melt pool as the additive manufacturing is occurring. And we're able to extract this in real time and look at the surface, essentially. That's something I like. But what's true is we need new standards. So all of our standards at the moment are based on geometry. What does exist, but really that's not what we're interested in. What we're interested in is, does it work? And what are these new features that we're creating? and how can we create best practice and how traceable the measurements. And NIST have come up with a roadmap. So this is basically the structure of the ASTM committee F42, which essentially is the AM committee, which is good because it feeds directly to ISO. And there is a subcommittee on medical devices within that, as well as the general medical device committee. But this, it still doesn't necessarily address everything at the moment. And so when we're looking at associated metrology with additive manufacturing, what are we looking at? Well, we're looking at function testing, we're looking at post-process, we're looking at in-process, we're looking at XCT, dimensional, porosity, surface, the full 9 yards. It's very difficult. And my question is AM and CT a match made in heaven or hell? I love these guys a bit, although she's been a bit silly this week. But, you know, people have their own opinions, don't they? Everybody. So, you get different reactions from different people on this. Now, CT is being used more as a metrology tool. It's been a long established international conference in Austria, in the middle of Austria, where nobody wants to go, which is what we like to get to. And then there's DXCT in the UK, which we held in 2019. It's recently been held in Manchester. The only reason I put Manchester's splash thing up there was that it was really badly designed, because I designed it, and it didn't look as pretty as that. And so we have this idea of using CT as a metrology tool and actually using it to optimize it so that we can get good metrology information out. And so we look at something like here, like this cranial plate. Okay, and what we were saying is that, well, for good osseointegration, what we want is sort of what we call roughened re-entrant features. Now, what we mean by re-entrant features is essentially, it's like a flap or a sort of hook shape or something. It's got a top side and an underside. Okay, and these are really hard to measure, really hard to define. And so what we've started to do is we've created methods for actually extracting surface topography from CT. We've also come up with methods for basically extracting surface topography data from some of these weird features that are not flat. They're just like well, they're essentially freeform. And we've done not only we've done this, then we've managed to we've extracted the data we've run around Robin with MPL, Nottingham, and a few other characters as well. And we've included Padova and Leuven as well. And so we've shown that this can work. And yeah, we've got an example here of an Innovate project that I led on, that we were looking at very similar dendritic surfaces, but this was in a heat exchanger, so it's different views, similar geometry and similar issues. Now, this is actually made out of nickel alloy as well, so it's incredibly hard to image. And so what we did was we had to basically have to build a piece of, Nikon built a piece of hardware able to image this. We built a piece of software with Simpleware. We basically built their metrology module, or helped them build their metrology module, so that they can extract surface data from this part of the image, and then Hyde to build this. And this actually ended up, this was part of an aerospace project, but this ended up going into, I think it was Lewis Hamilton's Formula 1 car 2 years ago. This technology. So that's my claim. One of my claims has been involved. Wow. So yeah, not long to go. Richard wants a cup of tea, and I'm overrunning. So we've got one of the other things that we've looked at, and this is current PhD of mine that's just finishing, is we've been looking at the effect of surfaces on biofilm formation. So we use Staph aureus to start with, and really just looking at, again, going back to the problem that John said, really about, is there something about different orthopedic surfaces that makes them more prone to infection? And what we found was, yes, there is. This is a log scale. and these are colonies of snot. And so essentially, if you've got a plasma, what we found, plasma sprayed surfaces were essentially much more susceptible, as you can see there, for protection as well. As you probably much more susceptible to infection. So essentially, this is the first part of the work that Chris has published. I don't know if I'll put anything else up because we haven't published it yet, but and then we're following on from this and looking at how this propagates into some of our additive surfaces as well. So porosity is a big issue, and this is a project we did with Rationale, looking at the needle form for Parkinson's disease. So for those who don't know this, it's basically screwed into the skull, and drugs delivered through it periodically. And so these are have to be they have to fit, they have to work, and they have to be in situ for a period of time. And so this is very important that we have we can understand the porosity and the manufacturing process involved here. As you can see, essentially, as produced, these surfaces are actually quite rough. So the implication is that there will be porosity subsurface. Something else we've done, and again I am finishing honestly, is unfused powder detection. So what we've looked at is when you've got an additive manufactured component, it may not necessarily be solid, it may contain areas of either unfused or semi-fused powder within the structure. And we've created protocols for the detection of this. Actually, when we did this for industrial partner, we discovered that their Ti-64 actually had nickel in it because it was contaminated with Inconel, which they weren't very happy about. But essentially, this is important because, as we know from our work on metal hips, any sort of metal material debris in the joint space or coming into contact with tissues is not very used. Now, I appreciate Ti-64 is a photoelectronic, but nobody has really done a powder gun of Ti-64 into a human and see what happens. So we kind of want to avoid that if possible. Okay, I'm winding up now. So what do we consider to be state of the art right now? Well, you guys are producing what were called real-world test cycles and producing proactive, aggressive preclinical testing. That's correct. Okay, and it's really good to tie that together with good use of metrology, whether it's preclinical, in vitro, in vivo, other Latin words, okay, that are in italics. And I'm going to claim a little bit of this, right? So what I want to do is map the full orthopedics life cycle, okay, the full implant life cycle, orthopedics 4.0. You can have that as a conference style. New materials, we want to look at new materials and new manufacturing technology. And the thing that scares me more than anything else in the world is additive manufacturing in the operating theatre. I was talking to an orthopedic professor, surgeon in Austria, who was getting very excited that she was going to have a metal additive machine next to the operating theatre. And I literally said to her, take the plug off and talk to a lawyer. Because the liability moves away from the diffusing tippers and to you. Do you want that, given your massive engineering background? Okay, that really terrifies. That really terrifies me as a guy who doesn't think things are measured properly anyway. Now, MRI data is routinely used to create surgical guides, and this is great. This has made massive steps forward. You know, to look at individualized surgical guides for hip, for knee, whatever. My mum had this done. Okay, she had both her knees done by John Cena, RLH, this sort of thing. And she was treated like breathing. but yeah, so I know this works. John actually offered it to but they've written in my long screen, so I thought that anyway. But no, it was really good to see it work. Just when you see it work on someone, and I actually know how pages look beforehand, so it makes a big difference. Now we have these perils in development. Those of us who've been involved in metal things like that, we get scared because litigation has no hindsight. Okay, you know, everybody's watching everything that's going on right now. What's happening? And we have these non-compliance traditional GD&T, and really is the legal lens really stopping or stopping none or making more concerns? I don't know. It should, but then again. And there are many analysis tools now available. But on the plus side, I think we have a very proactive industry. I think industry is very, very proactive in wanting to be better and wanting to find new things. There is funding for research, development, and investigation. Everyone wants to understand these legacy issues. I don't make the same mistakes again. And there is generally a higher profile for research in this area, as if we get any higher already. There's definitely a higher profile for standards efforts, and we've got standards now coming online to help people to be able to compare apples with apples. And I think metrology is now sexy. That's my ultimate last selling point. Does anyone have a counterpoint to that? I will see them outside of the property. I genuinely think metrology is sexy. But we do have these challenges, whether it's GD&T, surface topography, parameters that we are now creating. We need these single device approval tests for these single devices, new materials, and are we going to approach the flexible rigidity of bone? I just want to thank everybody. All these people have contributed in some way, shape, or form to something that's been on here. Lots of people are on there, including the University of Leeds. Thank you. My host today. And I want to acknowledge the EPSRC, who basically fund our group and have done for about 12 years. So that should be nice to them as well. We're grateful for power and straight and all that stuff. So thank you for staying awake. It's been emotional. If anyone has any questions, or if I leave that time, thank you very much.